The lectures this week, so our lecture on countability was to introduce the algebraic numbers. And one of our main things that we wanted to do there was to talk about the relative sizes of these sets, because there have been questions on how to sort of visualize that. Now, having gone through that, I'd like to apply some of that. So this week is entirely on applications, eventually to robotics, but first to the geometry that we talk about in computation, namely computational geometry. So that will be today's lecture on Wednesdays, and there'll be no lecture on Monday, no class on Monday, because we thought you'd like to have a little time to work on the midterm. Traditionally, the midterm is during class, but in honor of that, we'll have no lecture on Monday. Now, I'm just going to edit my name here so I know what I'm talking about, and then we'll continue. All right, that's better. I'm just trying to figure out what is going on. Hold on a second. All right, we should be better now. Apologies. Trying to run the network at the same time as I do this. Let me spotlight my video and share my screen, and we can talk about our topic for today. Let's see. All right. All right, thanks for your patience. Please let me know if you can hear and see me, and if you can see the document camera.
Yep, you're all good.
Excellent. Good. All right, so let's have a little review of where we are. So the topic today is a topic that's at the intersection of computer science and applications that we call rational signs, as in sine and cosine, and computational geometry. And this has applications to robotics, and to motivate that, I'll even show some robotics videos, at least one video this time, some more on Wednesday. And I'll also give you a little taste of some topics in linear algebra, which you'll also study later, which are very important in computer science, mathematics, and also in machine learning. I also want to mention that in terms of the topics we're covering today, we have some incredible experts on the staff. So Abe is a rather famous researcher in the area of machine learning, and Alex is an expert computational geometer. The other TAs have many skills in these areas too. So feel free to reach out to them as well as me for questions about this material. So where were we before? So as a recap, last time we showed that the countable union of countable sets is countable. And that's a little bit surprising because the countable product of countable sets is not always countable. And we use that to characterize sort of a hierarchy of the integers that you might usually hang out with and be friends with. So we have the integers are a subset of the natural numbers are a subset of the integers, which are a subset of the rationals, which are a subset of the algebraic numbers. That's numbers that are the solutions to polynomials, the roots of univariate polynomials with rational coefficients, and that's a subset of the reals. And all of these guys are countable. Now, the reason I wanted to show you that, aside from it being important exercises in countability, is that many of the things that come up in engineering, applications, and science, and in computer science fall into this category: integers, rationals, or the roots of polynomials. Polynomials are ubiquitous in modeling. And if those things aren't countable, there's very little hope of getting good algorithms to reason about them and compute about them. So this is very good news for us. It means that because we're computer scientists, the world is our oyster, so to speak. So very good news, but how do we actually do that? So to remind you about these objects we're talking about, we can think of these polynomials as being things like this, a function from the reals to the reals, and it might have a graph like this. So already we're moving a bit into the real plane, R cross R. And an example of such a function would be a polynomial like this. And we've looked at objects like this that were essentially finite sums of these monomials and coefficients. And in this particular case, we're going to have all the coefficients be rational numbers. We write that as f, the polynomial, is in this object here, which is the ring of polynomials with rational coefficients and one variable x. Now, this is a strange creature, but you've already dealt with this in some sense, because we know how to add polynomials. And you did that when you did things like adding infinite series. Of course, subtracting polynomials is the same idea. And you know how to multiply polynomials. And the reason you know how to do this is because we had you do that for infinite series. If we could do it for infinite series, it's basically trivial for finite series. And so a ring is a mathematical object that's closed under addition, subtraction, and multiplication. It's not necessarily closed under division, and you can see that because you can imagine dividing two polynomials and getting something that's not a polynomial. For the purposes of this class, we'll not ask you what a ring is, although future classes will. You could think of this as a set, because every ring is a set of polynomials with rational coefficients and one variable. At any rate, given such a creature, we're interested in its roots. Those are the values of x that set it equal to 0. And what we did is we actually counted the roots of all polynomials. So we, so to speak, conceptually enumerated all polynomials of all degrees, collected all their roots, made that a set, big A like this, and we showed that that's merely countable, which is pretty neat in some sense. Now, there's been a lot of discussion about that among students asking questions, and someone pointed out a very nice point, is that for my proofs, I actually assumed something stronger than we needed. I assumed that it was not cool to have all these coefficients be 0. And it was pointed out that actually my proofs are stronger than I initially believed. If we have the leading coefficient be 1, there's no restrictions whatsoever on what these other coefficients can be. That's kind of a nice feature, that the proofs are robust. Now, these numbers have analogs to a type structure in Scheme. So if we think of types, and of course other languages, you might think of them like this. If you have numbers, there are essentially two kinds of numbers. There's exact numbers, and there's inexact numbers. And so built into Scheme, we have integers, we have rationals, and algebraic numbers aren't built in, but you can easily add these. And these correspond exactly, more or less, to computational versions of the objects that we know and love and have been thinking about. Now, inexact numbers are things like floating point numbers. And the reason these are inexact is because it's not clear that when you add them, subtract them, multiply, or divide them, and then reverse the operation, you get your number back again that you started with. So these are approximations to the real numbers, but they're not really the real numbers. And this is true of any language, not just Scheme. By the way, how would we actually represent, if we needed to, an actual number that was, say, x in the real numbers? Well, you do know how to do that. That could be a stream of integers. But that's a lot of work to represent a real number, so we often approximate. So basically, in terms of this division between exact and inexact numbers or types, Scheme and other languages do a great job, and the mathematical objects, integers, rationals, algebraic numbers, and so forth, do a really nice job of implementing the exact numbers, and we approximate somewhere for the inexact numbers like this. Okay. Now, one of the things that came up last time, and I was going to do anyhow, is Now that we know some things, how exactly is this stuff really used in science, engineering, and computer science? So in other words, how is our mathematics like this in general employed? So these are important for algorithms that interact with the physical world. And it's not taught in a lot of places, although at other universities it's emphasized more. Let's go back and have a little more terminology, and then we'll start doing an application that I'll develop over this lecture and next. So go back to our example here. We have this function, we can draw its graph in the plane here. This is the real plane r cross r, and it's this nice curve. So we're, in some sense, by asking where this crosses the x-axis, we're asking a question about curves in the plane. The curves are defined very nicely by these polynomials. Nevertheless, they're curves in the plane. And when we ask about points like this, like where does f of x equal 0, this is a very special privileged set of points. So basically, you can think of this as being a set like this, a set of points x in the real numbers, such that f of x equals 0. Now, this mathematical object which here is a set of discrete points, and notice that's why this is really discrete mathematics, even though the actual polynomial itself can be viewed in various continuous ways, in some sense. This object has different names, but here the name we'll use for that is the kernel. K-E-R, kernel of f. The kernel of f is the set of points on which it vanishes, pronounced kernel. And for example, if we had the case, as I've drawn here, that f is actually a polynomial with rational coefficients, the set of all kernels defines the algebraic numbers, as we did last time. So we just need that term kernel. That's the only new thing on the page. Aside from getting you comfortable with the idea of visualizing these curves as being defined essentially by the graph of these functions. Now, as we pass to the plane for more complicated curves, and the application will become clear, we need to sort of do more than just look at these sets here. We need to look at things like the plane, which is r squared. Now, obviously, if we take the integer square that lives in the plane, natural numbers, integers, the rational square, and of course the algebraic number squared. Algebraic number squared are pairs a comma b, where a and b are both algebraic numbers. Namely, a and b are both roots of polynomials. And of course, remember our notation here. For example, if I say the rational squared, I mean q cross q, right? Okay. So that's our setting. And remember that we have already counted these things. We know that these things are countable even when we square them. We know this is uncountable, squared or unsquared. And the only new thing from before is my declaration that these mathematical objects are the mathematical objects that correspond to these types in Scheme and other languages. I partition the types into exact and inexact. Most languages don't do that because they don't want to confess the computation is in fact inexact, but Scheme is honest with you, so it does that. And I've introduced this new name for the zeros, or roots of a polynomial, called the kernel, and we'll use this notation. Okay, so with this in mind, we now want to consider a fairly deep mathematical problem that then has an application. So like any mathematician, I'll start with the math and then give you the application in a second. So here's a math question. Examples and application to follow. So suppose I have a curve in the plane. And it's defined on two variables, f and x, y, equals 0. And this is a polynomial. So in other words, f of x, y now is a function. You can think of it as a function on the plane that gives you back a real number. And there are two variables now, x and y. An example of such a thing would be the curve defined by x squared plus y squared equals 1. By the way, what does this curve look like if I were to graph it?
A circle?
It is, it's the unit circle. Very good. So here's this curve. So I'm interested in the places where this function vanishes here. Now, of course, I've said that this is the equation that I'm interested in. How do I get to the function? Well, the plane is r squared, and so I view this as being f from r cross r to r, and it takes the point x comma y to x squared plus y squared minus 1. I'm interested in where this thing is 0. Okay. So all I've done here is basically defined a nice curve here, and using our new notation here, you can think of this in a couple of ways. This is the kernel of f. Remember the place where it vanishes. You can also define this to be the inverse image of 0. In other words, take 0 and pull them back to the points that make it 0. And just to be really explicit about this, this could be represented as a set of pairs, x comma y in the plane, such that f of x comma y equals 0. Good. All right. So we're interested in considering a curve like this. All right. Now, what our question here is, what do these solutions look like? Like, we can draw them like that. But we're interested in asking if these solutions, points lying in this curve, can be rational numbers, right? That's a pretty interesting question. So obviously it's not an insane question, because this point here is clearly a rational number. What's this point here? Vanishes means equal to 0. So what is this point here that crosses the x-axis for the unit circle? It is. It's 1 comma 0. Thank you, Vanessa. This point here similarly is 0 comma 1. So clearly there exist, for our circle, there exist points that are rational, but how many are there? So the question we want to have is, what are rational points on the curve? Now, there are lots of reasons to ask this question, and one way to visualize this is as follows. So if we look at a grid over the space, q squared, you can imagine a very fine grid that kind of looks like this. All these points here, each one of these points is the form AB, which is a rational number. So there certainly are rational points that are arbitrarily close to this curve because they're rational numbers. And since q squared is countable, that's a lot easier to deal with than the entire plane to think about this. So in some sense, by asking for rational points that are on these curves, we're asking for easier solutions because we know a lot about rational numbers. So someone asked, how would we write this down? The way to characterize this, in some sense, what we want here is we want the kernel of f, which are the places where it's 0, intersect with the rational numbers. So these are the rational points. How can we characterize this set? So basically, there are two issues here. One is, it turns out I can solve this for the circle. Mathematically, and I'll only allude to that in this class, there are more difficult functions, things like ellipses and things like that, for which it's rather difficult to solve this problem. But for the unit circle, we can sort of get at it. Another point that I want to get at is that suppose I have a solution here that's actually rational. What if that rational number is formed by dividing two numbers in lowest terms, and the denominator has a quadrillion digits? So given that the complexity of operations on numbers depends on the size of those numbers, that might be sort of undesirable. We might prefer things that look more like 1 and 0, had very small size, rather than things had enormous size. So there's some notion here of getting points on this circle that are actually rational numbers, but also not making them so large that they're hard to compute on. Okay, so to put that in other terms, what if these rational points, such as this guy here, are huge in the sense of having an enormous denominator? So consider, suppose we had a number like 17 over 100, 1001 factorial, right? If that is the x coordinate of this point, that might be sort of undesirable because to do operations on that, you'd have an enormous number to deal with. And by the way, you might ask, what is that number actually equal to? And how would you write that down mathematically? Okay, so in short, the mathematical problem here, and we'll go to applications rather shortly, is we can always define, let's just talk about inverses for a second. Suppose I have f from x to y for any spaces or sets x and y. And suppose I have a point, say y0 in y. I can always form the set y0, and I could just have any set like this, and I could take the inverse image of this. So let's just take a case here. Suppose a more general case. Suppose I have some set here, say b in y. And let's look at this situation here. So I have x here, I have y here, I have f going between them. I have y0 in here, and it's contained in a set here called b. So I can always define the inverse image on sets. F inverse of the set B is equal to all points x in x, such that f of x is contained in B. And obviously this also works for single point sets. If I say f inverse of the set y0, which is just a 1-point set, that's just equal for all points x in x, such that f of x is equal to y0. And so when we have 1-point sets, it's convenient notation, although you have to be careful to sometimes write this as f inverse of y0, with the understanding that the full inverse isn't always defined, but inverses in sets always are. So in other words, anytime you have a function like this, you can always ask, what's the set of points that hits that subset? This thing here is f inverse of the set B. And even when that's a 1-point set, it works out. So we have this notation here to say, what are the set of points that would say take you to 0? And this justifies this notation here. Okay, so in this, we have the following project, if you will. We look at the kernel of f, which is the set of points that maps to 0. Namely, writing this out again, this is a set of points in the plane x, y in the plane, such that f of x comma y equals 0. That's the kernel. And we're interested in computing the intersection of the kernel with the rationals. What are points of these are rationals? And we want small rationals, if possible, because huge rationals are hard to compute with. So we want z in the kernel of f intersect the rational squared, and z is small. I have to define what small means, but that's the idea. So why would we want to do a thing like this? Well, let's do an example of what this might look like in some sense and get a better idea of what this problem looks like here. So that's the sort of mathematical setup. Let's go into a little more detail. So let's draw a quadrant of our unit circle here. Which looks like this. And let's now take a 45-degree angle. And we have a nice triangle like this. Remember, this thing here is the kernel, the place of f. It's the place where the unit circle is defined. And let's look at this point right here. So what is this point equal to? What are the coordinates of this point? If this is 45 degrees and this is a unit circle. So this is 1
Square
there.
root 2 over 2, square root 2 over 2.
Exactly right. I'm going to write that as 1 over square root of 2, but you've rationalized it, which is good. So that's that point there. So this is a point that's in the algebraic numbers. It's not rational. And why? Because we proved that the square root of 2 is irrational, and therefore 1 over the square root of 2 is irrational. Okay. And you could prove this using Pythagorean theorem if you wished, right? A squared plus b squared equals c squared. So the main thing is that we might want to not want to deal with these algebraic numbers. We might not want to, we don't want to have rationals instead. So to kind of blow it up here, if this point here is our weird algebraic point, 1 over square root of 2, 1 over square root of 2, we know we can put a fine grid of rationals around this. These are just all the rational numbers. They can be as fine as we want, and this is q squared, so we can get as close as we want to this point. So there exist nearby rational points, but are any of them short in length? Now, another thing I want to do here is define just a couple of variables that will be useful. You probably know that this first coordinate here is the cosine of 45 degrees. This second coordinate here is the sine of 45 degrees. So we can, without loss of generality, just think of this axis as being c for cosine, this one here being sine. And I'll use that later. Okay. So what we're interested in this case is we're interested in finding, here we have c and s again, right? C comma s. We're interested in finding cosines that are actually rational and sines that are actually rational. So that's what we're trying to get at here. All right, so that's our problem. Okay. So I have, now you've been very patient and I promised you applications, so I'm going to edge into that a little bit now. So I've claimed that finding rational points on these polygonal curves or these polynomial curves is a fairly deep math problem in general. Not as deep for the unit circle, but deep enough for this class. In general, it's quite deep. But what are the practical applications of this? Why would you ever want to do such a thing? So one place this comes up is called computational geometry. So these are algorithms that compute things about the geometry of real or imagined worlds, like graphics, physics, simulations could be imagined. So of course it includes fractals, problem set 1. It includes robotics, physics, computer graphics, space exploration, all of engineering basically, animation, protein structure, biology, drug design, all these things have actual physical dimensions and geometry. Now, one way of thinking about this is that algorithms in computational geometry often use the same model of complexity that we used in analyzing some of our recurrences and other simple graph algorithms. So the model of complexity needs to be developed a little bit. So the complexity model that's often used is called the real RAM model. And RAM stands for random access memory, which will become a little clearer as I develop what this model is. And we've been using it. So the first thing is that this model assumes that exact real numbers, and exactly with no degradation in precision, can be stored in and retrieved from memory in constant time. So assume, store, retrieve, real numbers, which are exact in order 1 time. And the second thing is it assumes that what I'll call the field operations, and this is times divided by plus and minus, and also square roots, and also sines and cosines, are also exact, and they can be computed in constant time. Assume times divided by plus and minus, also square root, and cosine are exact and constant time. And a terminology you'll hear sometimes, these are sometimes called the field operation. And the reason is that a mathematical object that's closed under these operations is called a field. When you do any of these operations to two objects that are numbers, you get another object of the same type back. And we use this model to develop asymptotic complexity. So these are the assumptions underlying your exploration of asymptotic complexity in 201 and in this class and in most of 330 that you'll see, namely that it doesn't matter how long numbers are, you can store them exactly, and computations on those numbers are also exact. And it's a pretty decent model in some ways to think about. So does this model work? Well, sometimes surprisingly well. And in the cases we gave you, that's true. But in geometry, you quite quickly get into trouble with this model. And I'm going to show you how you get into trouble. Basically, many applications in scientific computing, AI, robotics, and so forth, require that these exact operations or algorithms be mixed or interleaved with operations that destroy exactness. And this is an issue for these algorithms. And one of the things that can, in principle, destroy exactness is rotation. So one of the issues that comes up is how to deal with rotation. And for those of you who've taken some math classes or calculus, the perspicacious student will notice that rotations often involve sines and cosines. We have some sines and cosines even here. You can see that sometimes they can be irrational. That can be a problem because if you are multiplying by rational and irrational numbers, you might destroy the exactness of your computation. So to motivate what I'm going to say about rotations, I'd like to show you a brief video of some robots. Now, this is actually a video from my lab, and it focuses actually on distributed algorithms and parallel algorithms. But there are a few things to be learned here. One is the two students working on this. There's Daniela Roos, who's now the head of CSAIL at MIT. This is when she was a postdoc in my lab. And there's Jamie Jennings. And he's now at NC State as a professor. Now, one of the reasons I try to put a human face on some of the mathematics and computer science we do, because it's interesting to know these people and know who they are and realize that there are origins of what we're doing that are actually in people. What I'd like you to look at here, the only thing you really need to know from this, at least halfway through the videos, you'll notice that rotations are happening a lot. The robots are rotating. And that's going to be important to justify and motivate what I want to do next. The second thing is that although this video is kind of old at this point, it's actually a fairly difficult robotics problem. And if you went into most robotics labs at Duke or elsewhere and tried to just code this up on the robots, you'd find it complex and difficult. So it's actually solving a practical, hard problem, although a problem that's really a demonstration. So let me go over to the, let me go over and play this video for you, and then we'll come back and we'll talk about how we deal with rotations. All right. I'm back. Share the screen. All right, this is fairly short. Take a look at some actual robots, and then we'll come back. Let's see.
We are working on cooperative manipulation, for example, pushing a large object using multiple mobile robots. In this segment, the Cornell mobile robots cooperate to push a couch across the room. We have analyzed 3 different pushing protocols that require different amounts of synchronization and sensing. A more difficult task is the reorientation of an object to a desired pose, especially by robots that use line-of-sight infrared communication. Here, we demonstrate a parallel reorientation algorithm that requires no direct communication. The task is to push the couch through the door, which is on the left. The robots are to rotate the couch 270 degrees counterclockwise, so that the side of the couch nearest the camera will be facing the doorway. Tommy, the short robot in front of the camera, and Lily, the tall robot in the back, run the same reorientation program asynchronously and in parallel.
The robots sense the object's orientation locally using rotational odometry and 8 discrete contact sensors. The reorientation is accomplished using what we call pushing tracking steps, in which the robots push along a direction that is 45 degrees from the local face normal. Pushing along this direction proceeds until either the end of the face is detected through loss of contact or the robot's internal torque limit is reached.
Here we speed up the videotape by a factor of 4.
If the end of the face is reached, the robot reacquires contact by backing up. If instead the torque limit is reached, the robot attempts to locate the end of the face where there's a better lever arm for more effective pushing. Here both robots recognize the completion of the reorientation phase independently.
We're now back to normal speed.
At this point, Tommy's job is to locate the side of the couch opposite the doorway so that he can push the couch out of the room. He does this by first aligning to detect the couch's current orientation, and then by using his sonar, he moves parallel to the side of the couch until he locates the end, where he can rotate into pushing position.
Boss, open the door. Hey, we forgot to say that the couch has no wheels.
All right, so we're back. Let's go back to the screen, talk a little more. Okay, so what I wanted to convince you, in addition to giving you a little bit of computer science history.
This is Duke University.
Oh my goodness. We're going to stop that right now.
These dancing robots are twirling.
Okay, sorry about that. The video continued with another video. Can you hear me and see me now?
Yep.
Okay. Sorry, I only wanted to show you one video. You can look at the rest, they are on the website. So the main thing to take out of that is that these are actual robots. They're running control programs and planning algorithms, and they need to rotate. So we need to deal with rotation somehow. Now, the model we've been using so far, which we've just renamed to be this real RAM model and outlined some assumptions, it's actually a really good model, right? But in geometry, you quickly get into trouble with this model. So many applications, as I mentioned, in robotics, for example, but also AI, scientific computation, require that the exact algorithms be mixed or interleaved with these operations that destroy exactness. And what does that even mean? How do we think about a thing like that? So an example would be rotations. So suppose we have a situation like this. Suppose we have 2 sets of polygons, like a map, in the plane. Right, we have a polygon here called B, and we have a polygon here like this called A. Okay, fine. And these model actual objects in the world. And of course, these are infinite objects, right? If B is a table, you wouldn't want to just have the boundary because you might want to set your coffee mug on top of it and not have it fall through. So these are infinite objects, but we can represent these compactly just by using the coordinates of their vertices. And we can use rational numbers for those coordinates so they're actually exact. So there's no approximation involved. So the way to think about this, let's assume, for example, that B is sort of an obstacle, or something to be manipulated, and A is a robot, a rather strangely shaped robot, but stranger things have happened. And each of these vertices has a coordinate xy, which lives in the rational squared. So we can represent these coordinates as a list of vertices. For example, the coordinates here might be represented by a list x1, y1, x2, y2, x3, y3, all rational numbers. So a list of vertex coordinates like this. And of course, we can implement this nicely in scheme by saying something like define A to be the following list, 0, 0, and let's say 10/3 minus 3, and 5 minus 1, and so forth. So notice all the vertices are rational numbers, or in rational numbers squared. Okay, so far so good. We have an idea of what to do here, but we have to talk about what it means to rotate these things, because in the real world, they have to rotate to do their tasks. So suppose we want to take the robot, so-called robot, this triangle here, A, and we want to rotate it by, say, theta degrees and obtain something like A of theta in some sense. So in other words, for each vertex xy of the robot around some origin, we want to compute a new x prime, y prime as follows. So let's sort of think about what rotations are, come back to our problem. I'll save this. So how do we rotate a vector in the plane? So here's our plane, and here's our arbitrary point, xy. And to motivate this, bring our paper back here, xy might be a vertex of the robot, right? It's one of the coordinates here. I'm going to rotate that by some angle theta, all right? So one way of thinking about this is we have a vector to the origin like this, and we'll define what it means to rotate this by saying, if we want to rotate this by an angle theta, it's going to be up here like this. So this is the rotation, which would be some arc. This is x prime, y prime, and this is the angle theta we're rotating this to. So this corresponds to the operation where we're going to rotate the point xy by an angle theta about the origin here of the plane. So to do this most easily requires just a little bit of linear algebra, which is good for you to see. So in 2 dimensions, every rotation can be represented by a rotation matrix, which has the following form. Big R of theta. This is called a rotation matrix. Rotation matrix looks like this. Cosine theta minus sine theta, cosine theta. Good. So this rotates column vectors by means of matrix multiplication. And in our case, what we get here is we get x prime, y prime is equal to the following thing. Cos theta, write it out again, minus sine theta, cosine theta, and here's our original input vector x and y. So this defines what it means to rotate something, and you can also write it down in more familiar algebraic terms. The coordinates x prime, y prime of the rotated point xy by theta can be written like this. X prime is equal to x cosine theta minus y sine theta. Y prime is equal to x sine theta plus y cosine theta. Okay. So now we know a little bit about how to rotate something. Let's see if we can rotate an entire robot. So we know how to rotate a vertex instead. Let's draw our picture again for A. So robot A looks like this, and here it is like that. So let's imagine we were going to pick a point even in the middle, but it could be on the boundary, which I'll call A as a vector. So that's a point. So remember, you have an uncountable number of these points in the interior, lots of these things. So rotation of A can be described as some kind of mapping or some kind of image. So A, of course, is just a subset of the real plane like this. So we can define the rotation by theta of A as what? Well, basically we take this rotation matrix and we map it over all points A under bar to get the rotated thing. In other words, we take every point here, A, such that A is a point in the robot. And what we do is we apply the rotation matrix to it, like this, and multiply. So this basically can be thought of as a map operation. You take the rotation matrix here and you map it over every point like this. Now, and of course, every point A has the general form x comma y, just like here, so this makes sense. Now, of course, we don't, in practice, actually map a rotation matrix over the entire interior or even the edges of all these uncountable points in the robot A. And one of the beautiful things about computational geometry is that we have a finite representation of an infinite object, namely the ability to represent this infinite object here with all these points by an ordered list of vertices. Now, if A is represented by an ordered list of vertices, as we showed it was before, let's just page that back in. Remember, I have A represented by this ordered list of 3 vertices here, each of which is a pair of rational numbers. Then I can rotate the entire polygon A by merely rotating the vertices. So I can compute a representation of A of theta based just on these vertices. So to write that down in kind of algorithmic or scheme-like languages, suppose I have this object A, which is the real polygon. I can define an accessor called vertex. That just gives me the vertices back. This should give me 0, 0, the first point, 10 thirds, the second point, -3, and 5, -1. So I get the vertices of this thing. Suppose we say let the rotation operator in scheme be defined by rotate A by theta. Mathematically, this just denotes the function that performs the operation R of theta applied to A. Namely, we've just written a scheme function or posited one that does this operation here. So the vertices of the rotated robot A of theta are now going to equal to map lambda over points A, rotate A by theta over vertices of A. And now we can rotate our robot around. So this is great. We have a computational representation of a motion of a robot by rotation. And going back to our example here, this models a physical rotation of A with respect to B. So for example, if theta was negative, this might result in something that looked like this. This is A of theta, where this represents the angle theta. And this is the new rotation here. If we're rotating around, this is the origin. So we've modeled a physical rotation of the object A with respect to B. But herein a problem arises. And the problem can be seen from the equations. And the problem is, and you can sort of see that by going back to our picture of the unit circle, which I painstakingly developed with you. So the problem is, if you use this as cosine and this is sine, for almost all theta, 1 of sine theta or cos theta is irrational. In other words, it's a real number that is not a rational number. So this is highly problematic, right, for the principle of exact numbers. So for almost all theta, look at your thetas here, 1 of sine theta or cos theta is irrational. So it's difficult to represent arbitrary irrationals in computing machines. We'd rather use rational numbers. And so therefore we have to approximate somewhere. But where do we approximate in order to do this? So one idea is to simply approximate the irrational sines and cosines here with nearby rational numbers. But the problem is the resulting information is no longer a pure rotation. Let me talk about what that means here. So idea 1, pick nearby to approximate irrational sines and cosines. Remember, irrational here means a member of the real numbers that's not irrational. So the problem with this is we no longer get a pure rotation. In mathematics terms, it's not called not orthonormal. So basically, we want A of theta, which is defined above. But what we get is something like this. 1 plus delta S times A of theta plus delta theta, where these are little deltas, S is here, where delta S and delta theta are small constants. Now, what does this mean here? So basically, this beast here is an unwanted scaling. And this beast here is an unwanted rotation error. So instead of A of theta, we get a robot that has been scaled, that has changed sizes. And we also rotated to a different angle than what we wanted. Now, in the days of not having a pandemic, during this lecture, I usually ask all the TAs to attend, and I bring them up to the front of the class in a chorus line. We can't do that today, but I will dance for you by myself. So here I am. Someone calls out an angle to rotate by, like 90 degrees, and I'm going to rotate for you. And now someone calls out another angle, say 180 degrees positive, and I'm going to rotate like that. And someone calls out minus 90, and I rotate like this. So one thing you'll notice as I rotate, and this is absolutely key, is that when I rotated, I did not change size. I don't change size that quickly, but rotating me does not change my size. However, there's control error. So when you tell me to rotate 90 degrees, I might have rotated 89.9 degrees or 90.1 degrees. That's a different kind of error. So when you look at this situation here, it's really quite disturbing in some sense. So this error, the rotated, i.e. delta theta, is not equal to 0. So believe it or not, geometers and applications people regard this as a good kind of approximation because it still models a nearby configuration of A, the robot, and B, the obstacle in the world. In other words, it's not exactly accurate, but it's physically possible. On the other hand, the rotated polygons, A of theta, they've changed size with respect to B. It's scaled. So geometers and applications people regard this as a bad approximation in that it's inconsistent with A and B being models of rigid objects that do not change size when they rotate. So if this is not equal to 0, this is sort of an inaccuracy that we can live with. If this is not equal to 0, this is impossible physically. And it will break downstream algorithms dramatically. So therefore, what we'd like to do is we want to ask if we can find rational rotation coefficients for some angle that's close to the one that's desired, that have small representations and don't introduce any scaling. So we really want to impose on here that instead of this, we have delta theta equals 0 as an absolute constraint. And we want to make this, in some sense, small. So let me just state our desiderata again for algorithm design. We want to ask if we can find rational rotation coefficients, that is sines and cosines, for some angle that's very close to the desired one. And we want them not to be too huge. So we can formalize this by having 3 criteria. This is very typical in algorithm design for how we would do this. We can break them down as follows. The first is accuracy. So in terms of accuracy, we want delta S to equal 0. So basically we want to make sure that this doesn't happen. We want delta S to not be equal to 0 because we don't want any scaling. And the second thing we want to have happen here is that delta theta is small. So the thing is that is really crucial is that this error in scaling is basically disastrous for geometric algorithms. But the error in rotation is tolerable if we keep it small because it models a nearby configuration in the world. Okay. The second criterion is efficiency. We want these coefficients, namely sines and cosines, which are in the rational numbers, to be small in size. Now, let me say what that sort of means here. So we say, we put the rational numbers in lowest terms, numerator over denominator like this. Now, the main point is that if these integers are enormous, the operations are expensive because the operations scale based on the size of these things. So what we want to have is the denominator d is small in terms of number of bits. So our criterion for a rational number being small is when you put it in lowest terms, does it have a small denominator? And that's what we need. Okay. All right, so we're doing pretty well developing this. Let's just push a little further and see what it would mean to clarify some of these points. So let me just add some terminology here. The case where we have constrained delta S equals 0, this corresponds in terminology to what I'll call pure rotations. These are rotations that change the orientation of the robot, but they don't change its size. So we would like to rule out the situation here where the scaling is not 0, while we'll tolerate a small amount of error here. Okay. So this is sort of a list of criteria by which we would like to develop an algorithm to deal with these problems. And I'd like you to think about that for next lecture, read some of the notes, and we'll try to develop it together as we continue on Wednesday. Let me give you a couple of tools to think about this. Okay. So one way to state this problem is let S equals sine theta and C equals cosine theta, as I did in my picture. That corresponds exactly to the picture where I labeled the axes that I'll pull back here. In this picture here, we all know that the coordinates of the point on the unit circle are cosine comma sine, so I just labeled this cosine and this sine here. So that's my points on the unit circle here. Then we're interested in rational solutions to the equation s squared plus c squared equals 1. Now, picking such a solution is clearly equivalent to picking a theta such that sine theta and cos theta are rationals. That's really what our task is. The difficult thing for us is that such theta values are often irrationals. In other words, theta can be an irrational number. And we don't have the freedom to compute them directly because it's very hard to represent things that are arbitrarily irrational numbers. So we have to be a little bit more subtle. So what I'll do is I will define a rational sign to be any rational solution to this equation here. And one way to think about this is imagine we had the following situation. Example. We want both the sine and the cosine to be rational numbers. And we have to specify both because of this kind of example. Note, and B, S and C must be rationals. It's not sufficient to have just one. Let's look at this example here. Let's look at sine of 30 degrees. What's sine of 30 degrees equal to? Anyone know? Who knows what sine of 30 degrees is?
One half.
Good. Excellent. So one way of thinking about what the cosine is without even thinking about that is if we define a function, I'll call it omega of x to equal to the square root of 1 minus x squared, we can say the cosine of 30 degrees is equal to, let's call this x here, omega of x. So the cosine is equal to what? So now this height here is 1/2.
Square root 3/2.
Yep. So this thing here is an irrational number. So we can't just have one of these be rational. So in this definition, 1/2 is not a rational sign because the corresponding cosine is irrational. So what do we do about this? So paid commercial advertisement. On Wednesday, I will try to convince you that we can approximate this well by 451 over 901. And again, this particular approximation is not exactly a half, but if that's the rational sign, the corresponding cosine turns out to be rational, and we get something that's fairly nearby. So this is pretty neat. So this is for Wednesday. Let me just summarize this. Not a rational sign. And to take our definition here, a rational sign is any, say, sign in the rational numbers such that omega of s is a rational number as well. These are equivalent definitions. We either say S and C are solutions to this equation that are both rational, or you can pick one that's rational and make the corresponding cosine ensure that that's rational as well. Okay. So this is what we want to be able to get at when we reconvene on Wednesday. So I want to just give you a peek of the kind of theorems that we can prove. So how do we get at implementing, something that has this spec? Like, what does that actually look like as an algorithm? So I won't give you the algorithm today, although I will eventually give you code. But let's look at how what would actually be claimed in the reading. So what's claimed in the reading is actually very close to that. So in the notes, you'll see a specification like this. For a given angle, theta, and a tolerance, an error tolerance, epsilon sub theta, the algorithm returns a rational sign such that 1, delta theta, the angular error, is less than the tolerance. Sine inverse of s minus theta is less than epsilon of theta, so it's close by. The user says how close they want to be. The corresponding cosine, 1 minus s squared, is rational as well. And 3, s has at most 1 bit more than the shortest rational satisfying 1 and 2. So it's very short, twice as big as it has to be. So that will lay the foundations for understanding these algorithms. Let me motivate, as we close up here, why we're interested in the smallest possible numbers here, smallest possible rational numbers. So let's go to our definition of what this really means here. The length of a rational number is the magnitude of its denominator in lowest terms. The number of bits of S is the number of bits in the denominator. So we have two ways of measuring the size of these rationals, magnitude or the denominator. The magnitude of the denominator or the number of bits in the denominator. So what's the motivation between doing this? If we look at algorithms that do multiplication, division, and so forth, square root, cosine, and sine, all of these have a complexity that's a function of the number of bits. And they're typically between order n squared and order n cubed, where n is equal to the number of bits. So if you have rationals of the form n over d, and n over d is huge, that will be reflected in the cost of doing these numerical operations, which are typically between quadratic and cubic. So reducing and keeping the rational number small is absolutely crucial. Now, obviously, the number of bits is related to the number of digits, right? But we want to specify which one we're using. So in short, if we didn't have this criterion here, we'd be unhappy because we would get solutions that were enormous and very complex to compute with. We've already set the scaling equal to 0 by saying it's a rational sign, ice on there. And this specifies that our error in angle will be small. So given that now we know what kind of algorithm we want, we can talk a little bit next time about what kind of how to build up an algorithm, like how to think about it. Okay, so you've been very patient in trying to think about this. I'd like to now entertain you by showing you another video. So the video that you saw was a video that we made to describe our work. One of the things is that it caught the eye of a TV show that at the time was called Beyond 2000, kind of ironic since we're well beyond 2000 at this point. And one of the things that's interesting is that you can have a little lesson here on how they'll take your science and turn it into journalism. So I want to show you a little bit of what it looks like from our point of view. Let's take a look at this video from this television crew. There's one thing that's interesting here. It's hard to parse some of these videos because of the accents. So when Tommy was being pushed out the door, his speech synthesizer was hard to understand. And what he's trying to tell you is that we forgot to say that the couch has no wheels, which makes the problem much more difficult. Let me show you a couple of minutes of this, and then I'll come back and take questions and hang around after class for anyone who wants to do it. This is an example of what the journalists sometimes say about scientists. One of the things is that this particular journalist is actually from New Zealand. And in New Zealand and Australia, the term for furniture movers is removalist. So when she talks about removalist, she's talking about people or robots that move furniture. Anyhow, let's take a look at this for a few minutes. I will certainly end it by 4:45, come back and take questions, and then hang around a little while if you want to ask me any questions. All right, share the screen. over here. Here's Beyond 2000, a little spiel on robots, and you can see how they chose to portray it.
The idea behind the Industrial Revolution was for machines to do more work so we could do less. Okay, so it didn't exactly work out. But then along came the computer age, and the promise of combining the strength, stamina, and precision of a machine with the brains of a microprocessor. It would be called a robot, and eventually it would liberate us from much of the drudgery which we call work. Well, here we are. The 21st century is fast approaching, and you still wouldn't trust a robot to move your furniture, much less diaper your baby or mix a decent martini. Well, Caroline has found out that when it comes to robots, things are looking up.
Thanks, guys. No, they're not removalists. They're actually scientists who are developing a software package that will allow robots to perform the kind of complex teamwork that it took to get this couch here. Now, that may look easy, but to reproduce it is actually a very tricky problem because teamwork involves some level of communication between the parties involved. And to achieve this with robots is not only costly, but it's also often very inefficient because if you want to add robots to the team, the exchange of information between them becomes much more complicated and it slows the whole process down. So the researchers at Cornell University have found a way of streamlining this whole task. Meet Lily and Tommy. Now, they may be a couple who are not on speaking terms, but they still make quite a team. These two represent a major advance in robot technology. Not only is their software and modular design a major breakthrough, but their doting creators say this duo does what no other robots and precious few humans can. They cooperate. Interaction like this may well be the next major step towards a truly useful helper around the home or office, so long as you don't feel like having a chat afterwards.
I have finished rotating the lounge.
Parallel computer programs give each robot an idea of what the other is going to do. They're also encrusted with sensors to gather information, not from each other, but from the object being manipulated.
Push the lounge.
Add the ability to accept voice or thought commands, and creations like Lily and Tommy could take over your life.
You could imagine saying, well, I wish my desk was over there, and having the robots, move it over while you're at lunch break. You could imagine having teams of robots cleaning up the lab.
Add a healthy slice of computer-style group interaction to mechanize marvels like Lily and Tommy, and the feasibility of usable teams of robots becomes more than just an idea.
If you think of the team approach, it naturally leads you to apply tools from computer science. So, for example, computer science has talked a lot about how we can take serial programs, so programs that run on a single machine and in a sequential fashion, take those kind of programs and automatically distribute them on a lot of cooperating computers, and then try to somehow enable this parallel program to accomplish the task more effectively.
Many of the techniques which have made computers cheap and user-friendly have also been applied to Lily and Tommy.
Oh, no, I didn't plug the cable.
Not only are their internal microprocessors easy to program, but their unique modular design means
All right, I thought I would stop things there. I have some advice for all of you all who are younger. That was obviously just taken a couple of years ago. If you have the chance to take lots of pictures of yourself while you're young, take them and save them, because no one will believe what you look like 20 or 30 years later. At any rate, I wanted to give you an idea of why we wanted to do some of this mathematics, which is actually used currently in a whole lot of different robotic systems, programs that make robots do better things. But I also wanted to show you a little bit of the history of how some of this stuff got developed and where it might be applied. So I'll continue this on Wednesday, and we'll actually go further in trying to develop an algorithm with this kind of specification. take a look at the notes. They'll give you some hints on how we'll do that. And I'll continue talking to you then. So at this time, I'd like to end the lecture, but I'm going to stay around and I'm going to take questions from anyone who would like to ask me anything about this or other things related to computer science. So thank you all. Hope you enjoyed the videos. If those are popular, we'll show more of those later in the class and on Wednesday. And I've also put those on the class webpage with the proper links so you can take a look at them now. Okay, thanks everyone. And please stay around if you'd like to have more conversations. I'm gonna pause the recording now and stick around to take any discussions you